Okay, hello guys. Hello everyone. We are going to continue with differentiable functions today with derivative and differentiable functions. So as you know, differentiability and derivative is one of the most important subjects in math. Also, the integral is the other one. The next week, I guess, we are going to talk about integral. This week, we are going to think about differentiable functions. So just like always, I would give you some questions and I would give you time to think about them, and then I would start solving them. So let's start. Okay, so the first question is about a function f say from R to R, which we know this function f is differentiable everywhere. Okay. We also suppose we also know that f prime as a function from R to R is bounded. Bounded means bounded both from above and below. Now we want to show f is so-called Lipschitz. So just to remind you, or if you don't know that, to tell you what does this thing mean, we say a function f is Lipschitz if for any 2 points x and y, for any 2 points x, sorry, if there exists a number, a positive number, like say m, such that for any 2 points x and y, here the domain is R, so we take these points in R, f of x minus f of y, the absolute value of difference of x, f of x and f of y is less or equal than m times x minus y. This means the function is Lipschitz. Now we want to prove this for a function f, which is differentiable and its derivative is bounded. So think about that for a few minutes, and then I would write the solution for you. Okay, so let me write down the answer. So the idea is to use mean value theorem. Mean value theorem says whenever we have a function f which is differentiable, we can look at its graph. Say f looks like this. Okay. So if you take 2 points, x and y, say this is x, this is y. This quantity f of x minus f of y over x minus y, as you know, this is the slope of this line passing through the points x and f of x and y and f of y. If you look at the graph, you would see there exists some point here, let's show it with C, such that if we look at C and f of C on the graph, the tangent line to the graph at that point is parallel to this black segment, which means this quantity here equals the derivative at some points. Okay. So we have the same thing for our function here because our function f is differentiable. So f of x minus f of y over x minus y equals derivative at some point c, where c is between x and y. Okay. Now, on the other hand, we know the derivative is bounded. So derivative being bounded means there exists a number like n, where f prime of x, its absolute value is less or equal than n for any point x. In all points, the derivative of the function is less or equal than this number n. So also here, if we take absolute value from both sides of this equality we have here, because f prime of c, well, c is just a point, f prime of c is also less or equal than n. It means f of x minus f of y, the absolute value, that over absolute value of x minus y is less or equal than n, which simply means the absolute value of f of x minus f of y is less or equal than x times n times absolute value of x minus y. So this number n here is the same as this n here, or the n here is the bound of the derivative. So the function f is indeed a Lipschitz function. So being Lipschitz is kind of, so Lipschitz functions are continuous, and but they are not necessarily differentiable. Also differentiable functions are not necessarily Lipschitz. But if the function is differentiable and the derivative is bounded, the function is Lipschitz. So that's the first question here. Okay. Do you have any question here? If not, we can continue with the second question. The second question is about, it's not about differentiability actually, it's a question about continuity, or maybe more accurately about discontinuity. If you have a function f from R to R, where f is a monotone function, so f is either an increasing function or a decreasing function. A very interesting property is that if you look at the points of f, which f is not continuous at those points, let's show it with these continuous points of f. Let this thing to be the set. I would continue in the next line, the set of points x in R, where f is not continuous at x. If the function f is monotone, we want to prove this set is a countable set. So by countable set at this point, I mean it's either a finite set, or even if it's infinite, it's a countable infinite set. It has countably many points. It's not uncountable. Okay, it's a very famous and interesting question. Think about it for a few minutes again, and I would solve that after. Do you hear the rain? The sound of the rain? I was thinking it might be good. It might be relaxing, or it might be a noise to you when you hear it through the headphone. Okay, so the proof here is quite similar to another theorem you have seen before. If you remember, so recall, if you remember, every open subset of R, every open subset of R, like U, can be written as union of countably many intervals. Okay, so open subset of R are like this. For example, negative infinity to 3, union 5 to 7, union, I don't know, 8 to 10, maybe union infinitely many things, but they're countable. And if you remember why they are always countable, the reason was that we said we should first show any open set is really like U, is really union of, maybe U wasn't the best letter. Let me change that because it looks like union. Let's show it with V. Any open set V is union of some intervals, alpha, over some, we are taking union over some alpha. So it's a union of a lot of intervals. The reason why there are countably many is that inside each of these intervals, for example, in our example, these are these intervals, we can choose a distinct rational numbers. We can choose, say, R1 here, R2 here, R3 here, and these rational numbers are distinct. So Ri is not equal to Rj when I is not equal to j. On the other hand, the rational numbers themselves, they form a countable set. So there are at most countably many different rational numbers. And of course, because we assign a rational number to each of these intervals, there have to be finitely, countably many intervals. Now the proof, I would erase this thing. Now the proof of this theorem in the question, is quite similar. So, okay, let me erase this. So for example, suppose f is monotone. Suppose f is increasing. For decreasing functions, it's quite similar. F, we can look at the graph of f. The graph of f would be something like this. It might not necessarily be continuous. There are discontinuity points. So it would be like that, right? At the points of discontinuity, so I'm showing them with red dots. There are some gaps, as you can see. For example, there is this gap here assigned to this discontinuity. To this discontinuity, we can assign another gap. Here we have another gap. Here we have another gap. Do you see? So each point of discontinuity like x, so if f is discontinuous at x, say this is, for example, this is a point x, we can look at limit of f, maybe let's show it with x naught. We can look at limit of f when x goes to x naught from, say, above. Okay, show this number with a. And we can look at, maybe it's better to use b as notation. We can show it with b. We can look at limit of f of x. When x goes to x naught from below, we can show it with a. It's quite simple. I would leave this as an exercise to you to show when f is monotone, these limits, they really exist. They are the right limit and left limit. Okay, so when we look at the point x naught, there is limit from left, which at this point, this is limit from left. I'm assuming this number is a. And then there exists a limit from right, which is this number, which I'm assuming it's b. And this gap, this blue gap, which I'm showing it here, this gap is actually equal to the interval from a to b. So if we look at the y-axis, each point of discontinuity gives us an interval here. That interval corresponds to the gap at that discontinuous point. So discontinuous points, they are in correspondence to some intervals, which those intervals are gaps at those discontinuous points. Now, inside each of these gaps, we can choose a rational point, a rational number. I'm showing, for example, I'm showing that I'm denoting them with red dots. So inside each gap, inside each interval, we can choose a rational number. So to each interval, we assign a rational number. On the other hand, there are countably many rational numbers at most. So there has to be countably many of these intervals. Therefore, there are only countably many discontinuous points. Therefore, the set of discontinuous points of f is countable. It's not possible to have uncountably many discontinuous points. Is it clear? Is there any question here? Okay. If not, let's continue with the third question. Question number 3. Suppose we have a function f from the interval 0 to 1 to r. And suppose f takes on any of its values, exactly twice. What do I mean by that? So the range of f is a subset of R. Let's show that with, I don't know, let's show it with A. A is the range or image of f. It is all the set of all the points f of x, where x is the interval from 0 to 1. Now I'm saying, suppose for any element we choose here, so why not, is any point for any point why not there are exactly 2 points, say x0 and x1 in this interval. There are exactly 2 points x0 and x1, which are different. There are exactly 2 points such that f of x0 equals f of x1 equals y. So if I look at the graph of the function, if this is the interval 0 to 1, and so the function has some range, so say this is the range of f, a. For any value y not here, if I look at this line, there are exactly 2 times that the function cuts this line. So there are exactly 2 pre-images for y naught. Now I want you to show f is not a continuous function. So this question is again about continuity. It's not about derivative, but this is also a very interesting question. Okay, think about that for a few minutes. Does anyone have any idea how we can solve this one?
Could you say that it needs to have a minimum and a maximum, but then that minimum or maximum needs to be repeated twice? So if it's continuous, there will be values close to the min or the max that you'll need to go to 4 times? Something like that.
Yes. So, yeah. So what Hugo says is almost correct. That's indeed the way we should solve it. Let me, well, repeat what he said. He said, well, we know any function on, so kind of let's do a proof by contradiction. So say proof by contradiction. So suppose f is continuous, right? The interval from 0 to 1 is closed and bounded. It's closed and bounded. I already told you the subsets of R, which are closed and bounded, we usually call them compact. Any function which its domain is compact, like the interval from 0 to 1, it takes its maximum and minimum. So f has max and mean. So look at its max. So say there is some, say this capital M is the maximum of f. So say M is max of the function f. F should take this value twice, right? Just like anything else. But then what Hugo says is that if this point is max, this point is also max, the function would look like that, or it has to look like that around them. It can't be constant because then there would be more than 2 points taking the value m. And then if we look at m minus epsilon, there are 4 points which the value of f at those points equal m minus epsilon. This is the way to solve this problem, but there's a small mistake here. Can anyone tell me what's wrong with this argument? We can't correct this argument, but there's a small flaw in this argument. So let's name these 2 points, x0 and x1, which f at those 2 points get. So f of x0 equals f of x1 equals f. Does anyone see what's wrong with this argument? So we already have contradiction. If the argument of Hugo is correct, we have contradiction because there are 4 points taking the value of m minus epsilon, which is contradiction. Yes, so Nicholas is right. What if those 4 points, what if the maximum happens at the boundary points? So, okay, let me erase everything. So the flaw with the argument is that what if, Hugo is right. So I would explain what you said afterwards. So if this is m, Nicolas says, what if the maximums happens at these 2 points? So the function might be like this. And therefore, even if you look at m minus epsilon, if the max happens at the boundary points, everything would be fine. So you are right. F has max, say m, and there should be 2 points taking on that value, and they have to be the boundary points. So f inverse of m, this set must be equal to boundary point 0 and 1. So f of 0 equals f of 1 equals max. But you can do the same argument about, well, as Hugo corrected and completed the argument, I think maybe you also mentioned that first time. I didn't understand that. You can also look at the minimum points of f. F also has mean. Let's call that small m. Same argument tells us if we have mean somewhere like that, we can look at small m plus epsilon, and there would be 4 inverse points, which again doesn't make sense. So the points, the inverse image of m, the points which their values should be equal to m, they again, just like the previous case, they have to be the boundary points. So f of 0 equals f of 1 should be equal to m. Well, looking at these two things at the same time, it means max should be equal to mean, which means f should be constant. It means f is constant because its max is equal to its mean. Therefore, all the functions 0 to 1 just goes to one value. And this is contradiction. We were assuming it can't be constant. We were assuming that any point in the image has exactly 2 pre-images. So that's contradiction. Therefore, f can't be continuous. And that's it. Yeah. So any question here? Okay, so let me erase this and write down the next question. Okay, the next question is about derivative. It's an easier question. Say we have a differentiable function from R to R. F is differentiable. Suppose f is an even function. By that I mean f of minus x equals f of x for any x in R. Prove f prime as a function from R to R is an odd function. Okay, think about it for a few minutes. Okay, let me write down the answer. So we want to show f prime is an odd function, which means f prime of minus x equals minus f prime of x for any x. So f prime of minus x, by definition of derivative of a function, is limit of f prime at that point, which here is minus x plus h, minus f prime of x over h, when h goes to 0. Right. And this is equal now, since, sorry, there is no prime here. So since f is an even function, f of minus x plus h is equal to f of x minus h, right? Because it doesn't matter if we change, and this is also minus x. Also, f of minus x equals to f of x. So this thing is equal to limit of f of x minus h minus f of x over h when h goes to 0. But here, if instead of h we write minus h, we write k. If we do change of variable, we would get limit of f of x plus k minus f of x over minus k, where k goes to 0. If h goes to 0, k would go to 0. Minus can come out of limit, so this is going to be minus limit k goes to 0 of f of x plus k minus f of x over k. And this is minus, by definition, this is derivative of f at x. So f prime at negative x equals minus f prime of x, which means f prime is an odd function. Any question here?
Does this have anything to do with the chain rule?
No, no. Well,
sort of take
so, yeah. So the one, yeah, you're definitely right. So another, we could think about it slightly differently. So you're right. I could use chain rule. I could say so in order to compute f prime at well, let me see. I could use chain rule by, I think so. So let's see. I could look at the function which first sends x to minus x, and then I could look at the function which or say, yeah, and then I could look at f, the function which sends any points to its f, right? And then derivative of f of minus x would be derivative of what I have inside by chain rule, minus f prime of minus x. So f of minus x prime is minus, okay, so maybe one thing I can do change a variable. So rather than, I can take x to be minus, say, a. So I would have f of a prime would be minus f prime of a. No, it doesn't work very well, I guess. I think well, at least in what I wrote in the previous page, we didn't use chain rule. But we might be able to use that too. Let me think a little more. Well, at this point, see, the point is that this thing is not equal to f prime at minus x, first of all. So this is the derivative of the composition function, which is equal to minus f prime of minus x. No, I don't see that, because using chain rule, I don't see how we can use the function being even in the chain rule. So my guess would be no. It's independent of the chain rule. Okay, let's continue with The next question number 5. Using mean value theorem, estimate square root of 101. Okay, think about that for a few minutes. Okay, so mean value theorem says for differentiable functions, f of x minus f of y over x minus y is equal to derivative of a function at some point c between x and y. Now here, the function we are interested in is the square root of x. The x which we are looking for, its f is 101. We should choose a nearby point y. And here, that nearby point is 100. We should choose a point y where we know what is its f. So we are looking for f of x, which is square root of 101. But we know what is f of y, which is square root of 100, which is 10. So mean value theorem says f of 101 minus f of 100 over 101 minus 100, which is the square root of 101 minus 10 over 1, is equal to derivative of the function. Well, we know f prime of x is 1 over 2 square root of x. Derivative of function at some point c. Okay, but since c is between 101 and 100, square root of c is also between them. So c is greater than 10. Of course, the square root of 101 is less than 11. So just as an approximation. It's not a good approximation. It's something very close to 10. But let's just take it something less than 11. So 1 over 2 times c is something between 1 over 20 and 1 over 22. Therefore, square root of 101 minus 10 is between 1 over 20 and 1 over 22. Okay, let me erase here to write down the final answer. So if I add 10 to both sides, the square root of 101 is between 10 plus 1 over 22 and 10 plus 1 over 20. So it is between 221 and oh, sorry, I made a mistake somewhere. No, it's correct. And 221 over 22 and 201 over 20. This is a kind of range and approximation for the square root of 101. So this is linear approximation. This is kind of the most trivial approximation we can give for a function. We can use higher orders, and there are a lot of other techniques to find an approximation for a function. Okay, is there any question here? Okay, if not, let's continue with the next problem, which is the last problem. And it's simple and it's important. Suppose f of x, define f of x to be x to the x. And this is defined for positive numbers. So we are assuming x is a positive number. The question is, what is f prime of x? Just compute f prime. Okay, work on that for a few minutes. Okay, so I think the best way to solve this problem is to use chain rule. If you try to directly compute this thing, it might become a little confusing. So a better way to write down, a better way to rewrite f of x is to say x to the power x is equal to, well, equal to e to the log of x to the power x. Well, we know e and log, they cancel each other. So x to the x is the same as e to the log of x to the x. And this is one of the basic properties of log, which the power comes in front of log. It becomes x, log of x. Right. Now we can, if we define g of x to be e to the x, and h of x to be x log of x, you can see f of x is g o h of x. So first we have h of x is x log of x, and then g is e to that thing. It's here, it's e to the h of x, which is e to the x log x. Now chain rule tells us f prime of x is h prime of x times g prime at h of x. Now h prime of x, using product rule, we know the derivative here is derivative of first one, which is 1 times log of x, plus derivative of log, which is 1 over x, times x, which is 1. So here by log, I mean ln. Sorry, it's better to use ln. I mean, here the base is e. So times g prime, the derivative of g is itself, because e to the x, its derivative is the same thing. So g prime of h of x is just e of h of x, which is e of x log of x. So this is the derivative of x to the x. Okay, is there any question? Okay, if no, try to stay safe and have fun. Okay, that's it for today.